Kia ora koutou. I've just had a really great session about QR codes with some colleagues from DITA, and so I'm just going to use this as a time to record some of the ideas that came up and some of the things that we discussed. So the broad area that we're looking at here is error control, and how we control errors when data is downloaded, when it's stored, because it's on really fragile media, discs and CDs and DVDs and the internet and whatever is storing our data. It's incredibly small stuff that's incredibly fragile. So error control is needed to look after what's on that. Now, we're going to look at QR codes in particular, but just zooming out for a minute, there are three reasons that we code the data that we have. So chances are you've done basic data representation, that things can be represented using binary numbers. And then on top of that, there are three things that we alter those binary numbers. One is error control, where we add extra data so that if that data gets messed up while it's being downloaded or transferred, we've got a chance of recreating it, or at least knowing something went wrong. The second reason is encryption, trying to hide it from other people. And the third one is compression, trying to make the data take as little space as possible. And chances are all three of those are happening. In fact, if you're watching me now, maybe through YouTube or something like that, chances are all of those are happening because, of course, error control is being used to make sure the data you're getting hasn't been corrupted or messed up. Encryption is being used to make sure other people can't tell that you're looking at this very sensitive video. And compression is used to make it as small as possible so it downloads really quickly without overloading your internet connection. So these three forms of coding are absolutely crucial to the success of modern technologies. But we're going to focus on error control. And just to recap, this is not about all of error control, but what I'm assuming that you've probably had a look at, and I know a lot of people have been teaching this for a few years, is first of all perhaps error control using the parity techniques, where you have a certain number of bits and you make sure that that number of bits is, for example, an even number, by adding an extra bit to make it up to an even number, and that way if anything goes wrong along the way, you can tell because there's an odd number of bits and so on. And there's a magic trick that's really popular that uses that. So that's one form of error control, and that actually allows error correction, that you can actually figure out where the data went wrong and put it back right again. The other one that a lot of people have had a go at is checksums, and in particular things like product codes. So when you've got a product like this with a code on it, a barcode, 12 of the digits are the actual number of the product, and the last digit is a sum that's calculated from all of the other digits, and that way you can tell if it's scanned incorrectly in the supermarket, or if someone's made a mistake typing it in. And the idea of a checksum at the end is used for credit cards and bank accounts, passports, and all sorts of things. Now, that's capable of basically telling if someone's made a mistake. None of this is about security. None of it is really about making sure that someone hasn't put in a fraudulent number. The formulas for these are well known. You can make up credit card numbers that have the correct checksums on them and so on. So it's purely just making sure you haven't typed something wrong. And the third application, which you probably haven't looked at, but just to show you that this is quite a long-lasting thing, is the quantum computing, which is a new model of computing that people are really struggling to get it working properly, and the reason that it's a real challenge is errors, that these quantum bits, binary digits, are really unstable, and so they have to have a lot of error correction applied to them. My main point, and you won't want to cover that for NCA, but the point is that error control's been around since credit cards and earlier, that algorithms for checking that data has been stored correctly. And it's going to be around for a very long time because probably the next fancy computers are going to be very dependent on it as we use more and more, unstable is perhaps not quite the right word, but delicate technologies that we absolutely will need error control for. So the overall challenge of error control is that small unintended changes to your data, that whether it's being stored or transmitted, we want to either correct them or at least detect if there's been small changes. If someone's typed in their bank account number wrong, they swapped a couple of digits or typed one of the digits wrong, we don't want that to have big consequences, that they put money in the wrong account or something like that. Or if you download your students' grades, and one binary digit gets changed, and a student gets changed from an excellence to a not achieved or something like that. You don't want those sort of consequences just because one little thing changed. And so error control is detecting whether that happens. Also want to talk just briefly about what it isn't, because I've seen this misconception a wee bit. So first of all, it's not errors in a program. They're called bugs, and sometimes, it's fine to call them an error, but error control is not about fixing bugs in programs. We also get human errors when people are using interfaces. They make mistakes, and we try and design interfaces to prevent people from making those kind of errors. Again, this is not what we're talking about here. We're talking about data being corrupted by what is technically called noise, things that interfere with the data. Also just want to sort of introduce the two main forms of error control. So FEC and ARC, which sounds like you've dropped something on your foot maybe, but FEC, forward error correction, is where we add extra information into the data to make sure that when it arrives, it can be decoded and it can be even corrected back to what it should be, even if it's been changed a bit. Now, that happens, for example, with the two-dimensional parity, the magic trick, where the person actually manages to put things back to how they were. That's forward error correction. But sometimes you don't want to put too much extra data in, and an example would be things like a product code. It just has one digit on the end. That's enough for us to tell if a mistake's been made, but it's not enough for us to put it right. And so that's called a repeat request, because if you scan something and it doesn't work, then fine, just scan it again until it does work, and if it just won't scan, type in the number. So ARQ is used when it's reasonable to ask for the data again. If you were storing your data on a disk, or if it was being transmitted from deep space, they will use forward error correction, because if you go to read something off a file and something's gone wrong, you can't go back in time and ask yourself to store another copy of the file. Well, you kind of can, that's called a backup. But if you haven't done a backup, there's no way it can be reconstructed. So in that situation, we use forward error correction. We add more and more data to it to make sure that people have got half a chance of being able to reconstruct the data and not have to ask for another copy of it. So different things for different situations. And a lot of the theme of this is how much extra data do you add to it? I mean, for a product code, you could add twice as many digits, and that way all sorts of changes could be corrected because there'd be so much information there to help us correct it. But our product codes would be huge, and so it's always a trade-off of how much space we want to use up, how much data, versus how reliable we want it to be. And really good error control methods have a really good trade-off for that. So in particular, the focus of what we talked about today was QR codes, and they're really robust. By the way, don't scan this one. I actually accidentally scanned it today. We've just gone into level 4 lockdown, and this is the code on my office door. So if I ever get contact trace, someone's going to think that I was at work today. If you scan it and you're all over the country, then they'll think that people all over the country have been visiting the university today. That would be awkward. But anyway, my real point is, if you look carefully at this, it's been ripped. People have been going in and out of this door and rubbing against it and whatnot, and yet it still scans fine. And you can try this at home, and in fact, that's exactly what we did next. So what I've got here is my own QR code under a camera, and this one I've encoded a whakatoki into it, and if I scan it with my phone, then there it is. And that text that you can read there is encoded into the very obvious binary digits, the zeros and ones, the black and white squares that are here. And that's great. But of course, with this, we can really see the data. Normally you can't see it. It's in hard disks and being downloaded through the internet and that. But here we can really see it. And I'm going to take this particular bit here, binary digit, that white square, and color it in to a black one. Now you can try this one at home, and if you've got a camera in your phone or a barcode scanner, have a go at scanning it now. I'm also going to scan it, and it comes through exactly correctly for me, and hopefully it will come through for you. Now you might think one letter would change because I've changed one of the digits, but because of the error correction, the extra bits that have been added, it's able to put things right. And in fact, if you were using that parity trick, the two-dimensional parity, you can only change one and have that put right. With the particular method that's used here, in fact, there you go, I've changed a whole lot of bits and it still reads letter for letter exactly the same. In fact, one good challenge for your students is to see how many of these you can colour in. You can, again, try scanning that at home. Still scans, okay? And so do an experiment, just colouring in a couple at a time, and just find that threshold of where it goes from being able to scan it accurately to, still working, okay, to not being able to scan it. Okay, I'm just going to go nuts this time, colour in the whole thing. There, try and scan that. Okay, and now what's happening is it's scanning and scanning, but it's not finding the message there. And that is effectively an ARQ, a repeat request, because before it was doing forward error correction, FEC, by, I coloured in and it said, look, I can actually work out what this used to be, I'll show it to you. Now it just won't scan it, which is way better than going, I'll try and make sense of what this says and give you that value there. So the repeat request, basically it doesn't do anything, which means, okay, this didn't work. Whoever gave this to me, I'd go and ask them for another copy of it. If I was checking into a supermarket, the QR code on the door, chances are it'll work, even if it's damaged, if it's got a bit of dust on it, a bit of light reflecting off it, things like that, chances are it'll work. If it had got so damaged that it just wouldn't scan, then yes, I would have to go and do a repeat request, which would be I'd go to management and say, hey, your QR code's not working, you should replace it, and maybe I'd wait around for them to replace it before I actually do my scan. Maybe I'd try and find another copy of it somewhere. So that's sort of the big picture. Just for fun, one of the things I showed for a talk that I gave a while back, we made up this game called Will It Scan. So here is the game of Will It Scan.
We can use this idea to play a game that I like to call Will It Scan.
Will it scan?
Okay, so you don't need to deface QR codes because often they're already damaged. Let's try a few. Upside down. Ripped paper. Through 2 layers of glass. Can 2 people scan at once? Can you scan a camera that's already scanning a code? Backwards through glass?
So because QR codes are incredibly versatile and you can put them in all sorts of places, I found this one that's on the rooftop of a building, and in fact it turns out there's a few rooftops that have got QR codes on them. That might be something for your students to look for on Google Maps. You pretty much need to be an aeroplane to be able to scan those ones. But the interesting thing about this one, for example, is that it's got air conditioning and pipes and things in the middle of it, which are the noise that we have on any sort of data. The whole point of error correction is it can cope with things being changed. Don't know whether a whole air conditioning unit is what the designers of QR codes had in mind, but there you go. Now, let's have a look at the nitty-gritty of what happens, because for your students to really get into QR codes, it's not just a matter of having fun scanning them all, even though that reveals quite a bit about how robust they are. But how are they coded? And, well, the way they're coded is called the Reed-Solomon error correction method. There's a photograph of Reed and Solomon. They invented this in the 1960s, and it's been used for all sorts of stuff. It's been used for space exploration, because when you're transmitting data from space, a spaceship can take half an hour for data to get from space back to Earth, and you can't do a repeat request. You can't just say, oh, that's a bit messed up. Probably will be, because it's getting cosmic radiation on it. So you have forward error correction instead, and the Reed-Solomon code in particular works well for this. Also on optical media, CDs, DVDs, and so on, they use it. But QR codes make really good use of it. Lots of other stuff does as well. It's one of the most popular ways of doing error correction in practice. Now, the maths behind Reed-Solomon coding is pretty tricky. It's reasonably advanced. It's based on finite fields, and it uses polynomial equations. So basically, you're multiplying polynomials and using them as your finite field. Now, for kids that are really into maths, that's probably absolutely fascinating. But if they're not, there's an awful lot of numbers and formulas and things going around the place, and they don't need to understand it at that level. But there are some things that they can really get their teeth into with what's going on with QR codes, and I'll flick over some of those. So the first one is just the idea of code rate, that when we're adding bits to data, then we're sort of got that overhead. And so if we've got k bits of raw data and n bits in total, then we say that the code rate is k divided by n. Let me give you an example. If you've ever done the parity magic trick that's pictured here, there is 5 by 5 bits of data, so 25 bits of data, and then the magician adds another row and column, bringing it up to 36 bits in total. And so we'd say that that's got a code rate of 25 over 36, or 69%. 69% of those bits are actual data that we want to transmit. The other 31% are called overhead. That's stuff that we've put in purely for the sake of error correction. And if we weren't worried about errors, we wouldn't bother with them. We would just send the 25 bits because that would take less time. Here's another example. These students have put down, they had 9 by 9 cards, and they've added another row and column to bring it up to 10 by 10. So they started with 81 bits, the 9 by 9, and they brought it up to 100 bits. So only 81% of that has useful data. That's actually a really good code rate, but it's not very good error correction because this particular method can only correct one error. One bit being changed. With the QR codes, of course, I was changing lots of bits and it could still correct it. If you wanted, you could look at a product code. It's got 13 digits on it if it's in New Zealand. One of those digits is a check digit, so 12 out of the 13 actually carry useful data. It's got a code rate of 92%. That one can't do error correction at all. It can only detect errors. Now, with the Reed-Solomon methods, we can actually have a choice about what the code rate's going to be, what we get to pick n and k, and that can be based on how much error correction you want. So the amount of error correction Reed-Solomon will give you is n minus k over 2. In other words, n minus k is just the number of extra bits that you've added. So, if you add 100 extra bits, then it will be able to deal with 50 bits being wrong, 100 divided by 2. And it can detect up to n minus k, in my example, 100 bits of errors. Detection means repeat request. It knows something's wrong, can't put it right. So Reed-Solomon gives you this trade-off, and you get to choose n and k, or you have a lot of control over what they are. And QR codes likewise do this. So, for example, this is one of the simplest, I think it is the simplest you could do. They call them versions for QR codes, and there's 40 different versions, but it's basically 10 sizes of QR codes, depending on how much data you want to store in them, and each of those has 4 levels of error correction that you can choose between. Now, when I say you can choose, whatever's producing the barcode is going to, implicitly give you that decision. Most software actually doesn't let you choose. It just says, this is the level of error correction I'm going to give you. In terms of the size of the code, it's generally just going to give you the smallest code possible that will encode the amount of data you give it. Now, in this case, I think I only gave it about 6 letters. You can scan it, you can find out what I actually put into it. And so it didn't need a very big QR code at all. This is the smallest one. It's 21 by 21 dots. If you count the black and white squares, it's 21 across, 21 high. Now, 3 of them in the corner there, those 3 squares in the corner, they're actually for alignment, and they don't contain any data. That's just so it can figure out where the thing is on the page. By the way, one thing to watch for, if you mess with those, most software can't cope with it. It loses the alignment and it can't figure out where anything is. But in general, the actual payload of the data is the patterns in the middle there. At version 1, if you ask for a low error correction rate, it will only cope with 7% of it being corrupted. Now, that's actually a lot of that data, would be corrupted to get up to 7%. And the code rate there is 78%. In other words, 78% of those bits actually contain useful information, and the other 22% are there. They basically contain the Reed-Solomon codes that will be used if anything goes wrong. So it's a pretty good trade-off. You can mess with up to 7% of those bits, and you're only you're still getting 78% of them as being useful for delivering stuff. Of course, if you went up to 100% code rate, everything's valuable, but there's no error correction bits. So even one tiny error and it's all over. You've messed up with your data. And at the other end, if you only have about 1% code rate, it effectively means that you've got 100 copies of your data. It's 100 times bigger than it needs to be, but boy, is it going to be resilient to errors. Okay. So with QR codes, there's 4 levels of error correction: low, I think it's called medium, quartile, and high. Your students can investigate those and figure out for a particular QR code what kind of level it's got and so on. And so the version tells you how big it is and what level of error correction it's got. If they really want to dig into what's inside a QR code, then this diagram from Wikipedia has got a really nice example of one. And it gives you a sense of, it is a bit complicated what's going on inside these things. For NCA, they probably don't, this is around the boundary of where they really need to understand things, but it's kind of interesting. So this one here contains a URL, and these arrows show you the order in which the dots are read. So it's not even a cross or anything like that, it's zigzagging. And so here we've got www.wiki, it's actually the Wikipedia address. And so these are the characters here. I think there's about 14 or 16 characters. Each one is 1 byte. It'll be an ASCII code. And then these bytes here, E1 through to E7, each of those is part of the Reed-Solomon code, the error correcting codes that have been added to it. So those are the overhead. And so the rate, if I lost count here, but I think there's about, say, 14 bytes here, and there's 7 bytes there. So there's 21 in total. So 14 out of 21 is your rate, because it's about 2/3 of it. It's actually got useful stuff. About 1/3 of it is overhead that you're paying so that you can get error correction. Another thing just to note on the way is that whether you've got the black and white symbols, it turns out they don't correspond directly to 0 and 1. On an even row, then the dark symbol, black, is 0, and on an odd numbered row, it's a 1. So the meaning actually alternates as you go up rows, and I expect that's just purely so that if you have lots of empty stuff, it won't be totally blank. It'll at least have alternating black and white squares on it, so that the software using the camera has got something to go on for the actual shape of the thing. And then on Wikipedia, there's even more details. There's a whole lot of charts and diagrams showing you what every single bit in there means. Again, I wouldn't really go into that much detail. I think if you step back, the really big points is that your students need to understand why we worry about forward error correction versus repeat request, how things like QR codes allow forward error correction up to a certain point and then revert to repeat request, and just being able to reason about all of these things. Why do we have them? What are the limits? What might they be used for? What do they apply to, and so on? And how fundamental they are, because pretty much anything you do on a computer, there is going to be error correction codes being added. So just because you send 100 bytes of data, chances are there's 120, 180, who knows what bytes being sent. And the reason they're there, just to make your life less complicated. Chances are the data will be received okay. So those are the main things that we went over. Hopefully that gives you an idea of the sort of level that I think will be useful. The information, everything I've been talking about is in the Computer Science Field Guide. At the moment, there's actually a supplementary section on QR codes. We'll make sure that those links are posted with the video. And that's just because we're moving servers at the moment on the Field Guide, but soon it'll all be incorporated under error control in the Field Guide. And so, go explore, go and have fun messing with barcodes, QR codes. Make your own. Don't go messing with the ones that people have put on their doors for scanning and tracing. That could not end well. But enjoy the fact that error correction is making our lives better. Ka kite anō.